Good morning, everybody. Today we will have a very interesting talk. It's about black holes and Hawking radiation. Professor Dr. Fatemeh Mirekhtiary was born in Iran. She has been graduated from the physics department of the Gulian University. Then she has worked as a research assistant at the Energy and Water Institute of the Sharif University. After that, she has completed her PhD degree in the field of theoretical physics in Turkey. She served as associate professor in Near East University from 2007. As a theoretical physicist, her area of field is the cosmology, astrophysics, general relativity, and quantum gravity. She has many awards and prizes, and she is a member of many international scientific associations, and she has published a lot of scientific papers. So let us to welcome Dr. Fatemeh Mirekhtiary. Thank you very much.
Hello, Dilber hocam. Thank you for your introduction. You introduced me to everybody. Thank you so much. And let me get started if you don't have any question.
Please, go ahead.
Thank you so much. Excuse me, Barish Hoca, would you please show my presentation? Yes, thank you so much. Everything is okay. Now I'm talking about black holes and Hawking radiation. In fact, everybody, in this presentation, I try to answer some of our questions, such as what is a black hole, where do they come from, what happens if you fall into one. And after that, I'm interested to talk about Hawking radiation, Heisenberg uncertainty principle, and Schrodinger cat, and at the end of today's discussion, I'm talking about Einstein field equation. In fact, everybody, black holes are one of the strangest things in our existence. A black hole, in fact, everyone, is a place where gravity pulls so much that even light cannot get out. The gravity is so strong because matter has been squeezed into a tiny space. This can happen when a star is dying. Because no light can get out, people can't see black holes. They are invisible. Space telescopes with special tools can help find black holes. The special tools can see how stars that are very close to black holes act differently than the others. As you can see in this figure, everybody, a black hole has three different important parts. One is accretion disk, and the other region that we have to talk today is event horizon of a black hole, and the third important part of a black hole is singularity point. Today, everybody, we'll talk about all these three portions separately. First of all, I would like drive your attention to accretion disk. Accretion disk, in fact, is just a disk-like flow of gas, plasma, dust, or particles around any astronomical object, such as around this black hole. In which the material orbiting in the gravitational field of the object and loses energy angular momentum as it slowly spirals inwards. In fact, everybody, in astrophysics, the term accretion refers to the growth in mass of any celestial object due to its gravitational attraction. In this, I prepared everybody a short video for you that can show you and that give you an idea about accretion disk. This just disk-like flow of gas, plasma, dust, and particle. That would be a nice to have this video that is prepared by NASA. Let me have it in here. Yes, thank you for this nice video, everybody. In here shortly you can see the accretion disk around of the black hole, that how it can orbit around of the black hole. Okay, in this slide, everybody, I'm going to talk about the size of black holes. I'm going to answer this question: how big are black holes? In fact, everybody, as you can see in this slide, there are three different types of black holes: tiny black holes, stellar black holes, and supermassive black holes. In fact, black holes can be big or small. Scientists think the smallest black holes are as small as just one atom. These black holes are very tiny but have the mass of a large mountain. As we know in physics, everyone, mass is just the amount of matter or stuff in an object. Another kind of black hole, the second one, is called a stellar black hole. Its mass can be up to 20 times more than the mass of the sun. There may be many stellar mass black holes in Earth galaxy. Okay, I mean in our Milky Way, in fact. So the largest black hole that we know is known as Sagittarius A, as you can see in this slide. This black hole, in fact, have masses that are more than 1 million suns together. Scientists have found proof that every large galaxy contains a supermassive black hole at its center. So the supermassive black hole at the center of the Milky Way, everyone, is called Sagittarius A. And as I said to you, it has a mass equal to 4 million suns together, and it would fit inside a very large ball that could hold a few millions Earth. And also, everybody, currently the largest black hole that is found, as you can see in this figure, is called, S50014 plus 81. This is just the largest supermassive black hole known up to now, and it is 40 billion times of the mass of our sun, and it's 263 billion kilometers in diameters. Okay, in fact, this distance is very huge. That is 47 times the distance from the sun to Pluto. The next question in here, everybody, we are dealing with the formation of black hole. You can see in this figure, in this slide, we have the life cycle of a star. In fact, I'm going to explain how do black holes form. So scientists think the smallest black holes formed when the universe began. Stellar black holes are made when the center of a very big star falls in upon itself or collapses. When this happens, it causes a supernova. So what is a supernova, everybody? You can see a supernova is an exploding star that blasts part of the star into a space. Scientists think supermassive black holes were made at the same time as the galaxy they are in. Okay, let me review this process, everyone. In fact, we know that stars are incredibly massive collections of mostly hydrogen atoms, which collapses from enormous gas cloud under their own gravity. In their core, nuclear fusion crashes hydrogen atoms into helium, releasing a tremendous amount of energy. As you can see, everybody, this energy in the form of radiation pushes against gravity, and it maintains a delicate balance between the two forces. As long as there is fusion in the core, the star remains stable enough. But for the stars with more mass than our sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. But you know, everybody, iron is just the element that is not interesting to contribute into fusion. That's why, unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. So what happens? In fact, iron builds up at the center of the star until it reaches a critical amount, and the balance between the two forces, in fact, radiation and gravity, is suddenly broken. Then what happens? When it happens, as you can see, when the balance between these two forces, radiation and gravity, is broken, after that, in fact, the core collapses. Just within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created, as the star dies in a supernova explosion. This produces either neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. In fact, everybody, after all this process, as you can see in this figure, if mass of the star is in fact big enough, then it can we can have our black hole. Otherwise, it can be a neutron star. Okay, let me go to the next slide and discuss about black hole. And we are dealing with this question, everybody in here. If black hole are black, how do scientists know they are there? This is a nice question, and in fact, this is, we have to discuss about how scientists found our black holes. What is their effect in the universe? In fact, a black hole cannot be seen because a strong gravity pulls all of the light into the middle of the black hole. But scientists can see how the strong gravity affects the star and gas around the black hole. Scientists can study stars to find out if they are flying around or orbiting a black hole. When a black hole and a star are close together, high energy light is made. This kind of light cannot be seen with human eyes. Scientists are they are using satellites and telescope in a space to see this high energy light, in fact. So if you look at the black hole, everybody, what you would really seeing is the event horizon. Okay, you see in here, everybody, this region is known event horizon. Anything, in fact, what is it and what property does it have? Anything that crosses the event horizon needs to be traveling faster than the speed of light. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, everybody, what is the whole part of black hole? Actually, I can answer this question, and if you are working in this field, everybody, you can answer me quickly. In fact, the whole part is called the singularity point. And actually, I have to say you that I'm not sure what is it exactly. But we can say that a singularity may be infinitely dense, meaning all its masses is concentrated into a single point in a space with no surface or volume. I mean, it's just like dividing by zero error. In fact, everyone, mathematically, you know that if something divided by zero, it tends to infinite. Dividing, this is just an error, mathematically error. So when Einstein worked out about this subject, finally he reached the singularity point of black hole. That is something that is not clear, and we don't know what is it exactly. Okay, let me go to another subject. Let me talk about if what will happen if you fell into a black hole. In fact, everyone, the experience of time is different around black hole. In fact, from the outside, you seem to slow down as you approach the event horizon. So time passes slower for you. At some point, you would appear to freeze in time, slowly turn red and disappear. From your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of these two things. It can be quick death, and also it can be very quick death. Let me talk about this one, a quick death. What happens, in fact, if one falls into a black hole? In fact, everyone, we know that a black hole curves the space so much that when you cross the event horizon, there is only one possible direction. You can take this literally inside the event horizon. You can only go in one direction. It's just like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated that at some point, even tiny distances, just something like a few centimeters, would mean that gravity acts with millions of times more force on different parts of your body. In fact, your cells get torn apart like this figure. As your body estranges more and more until you would be a hot stream of plasma, one atom wide. So the second possibility that can happen, everybody, unfortunately, is a very quick death. In fact, very soon after one crosses the event horizon, will hit a firewall and be terminated in an instant. But unfortunately, as we know, neither of these two options are pleasant. In fact, everyone, a smaller black hole will kill you even before you enter its event horizon. As a rule of thumb, the further from singularity you are, the longer you live. Okay, let me talk about this figure, everybody, that is prepared by NASA again. This picture, everyone, shows the activities of the central black holes of Milky Way, which is called Sagittarius A, that is introduced to you right now today. This just shows the activity of Sagittarius A between from 2008 and 2013. In fact, it just compared these two status. So the large image, as you can see, contains X-ray from Chandra in blue and infrared emission from the Hubble Space Telescope in red and yellow. Okay, Chandra, everyone, I have to talk about Chandra telescope. This is called after Chandrasekhar, Indian physicist. I can say you that this is the third important physicist in the universe. If I just tell you just something in here, the first important physicist in this field is Albert Einstein. The second one that today I will talk about is Stephen Hawking, excuse me. And the third one, who is a giant in this field, is Chandrasekhar, this Indian physicist. That's why this telescope, in fact, Chandra, is called after this Indian physicist, Chandrasekhar. Okay, you see the inset. The inset shows a close-up view of Sagittarius A in X-ray, only converting a region half a light year wide. And the diffuse X-ray emission is from hot gas captured by the black hole and being pulled inward. This hot gas originates from winds produced by a disk-shaped distribution of young massive stars observed infrared observation. Okay, right now, everybody, we are dealing with another nice question. Could a black hole destroy Earth? This is a nice question, everybody. That may be a question for many people. Could a black hole destroy Earth? So the question is no. Black holes, in fact, do not suck things up like a vacuum cleaner. Black holes do not go around in a space and eating star, moons, and planets. Earth will not fall into a black hole because black hole, in fact, because no black hole is close. If a black hole, the same mass as the sun, were to take place of the sun, Earth still would not fall in. The black hole would have the same gravity as the sun. Earth and the other planets would orbit the black hole as they orbit the sun now. So then what will happen? What's your opinion, everybody? In fact, here I can say you that if we just take place this black hole, in fact, instead sun, we just would definitely freeze to death. In fact, but we will not fall into the black. But I have to tell you that the sun will never turn into a black hole because the sun is not a big enough star to make a black hole. This is just a good point that I have to say. So how is NASA studying black holes? NASA is using satellites and telescopes that are traveling in space to learn more about black holes. These spacecrafts help scientists answer questions about the universe. Scientists can't directly observe black hole, with telescopes. In fact, they can't directly observe black holes with telescopes and detect X-ray lights or other forms of electromagnetic radiation. But we can, however, infer the presence of black holes and study them by detecting their effect on other matter nearby. This is a nice subject, everybody, and if someone is interested, they welcome to this subject. I'm interested to work out about this topic. If a black hole, in fact, passes through a cloud of interstellar matter, for example, it will draw matter inward in accretion process, as we discussed. So a similar process can occur if a normal star passes close to a black hole. So in this case, the black hole can tear the star apart as it pulls it toward itself. As the attracted matter accelerates and heats up, it emits X-ray that radiates into space. Recent discoveries, everybody, offer some tantalizing evidence that black holes have a dramatic influence on the neighborhoods around them, emitting powerful gamma ray bursts, devouring nearby stars. Okay, by this introduction, everybody, we have understood that black holes are just space, are just a region in a space that gravity is very strong, that nothing, even light, can escape from the event horizon of the black hole. In this figure, everybody, we see quantitatively we have a black hole in here, and this region is just the event horizon of the black hole. But so we say that nothing can escape from the event horizon, and these are completely black. But here there is a paradox. In fact, this physicist, as you see, Hawking, proved that in fact in 1974 he published a paper in Nature, in fact, and he discussed about Hawking radiation. He proved that a black hole has a kind of radiation. So the paradox is that in here we say that nothing can escape from black hole because of its strong gravity. In another side, we say that no, there is a radiation that is called Hawking radiation. So my aim in here, everybody, is just to talk about Hawking radiation after the introduction about the black holes, and we know what is a black hole. In fact, classically we just described it. Right now, everybody, I would like to talk about Hawking radiation. I would like to describe what is it and where does it come from. Excuse me. Okay, you see this physicist, Stephen Hawking. In fact, everybody, I have to tell you that Hawking radiation is a form of black body radiation expected to be emitted by black hole due to quantum effect around of the event horizon. In fact, it occurs near the event horizon. This physicist, everyone, Stephen Hawking, created a scientific case for its existence in 1974, and it is named after him. We have to say that as powerful black holes are, they will eventually evaporate through a process that is called Hawking radiation. So to understand how it works, everyone, we have to look at empty space, and we have to talk about uncertainty principle. In fact, I can say you that this Hawking radiation is just a direct result of uncertainty principle. How it works? In fact, well, you have to think about, you have to look at the empty space. In fact, everybody, if you look at the empty space in the quantum view, in fact, empty space is not really empty. It's not 100% empty. There is always, according to uncertainty principle, there is always a small probability of creation of particles and antiparticles. In fact, I have to say that empty space, in fact, is filled with virtual particles. Let me see how this scenario works. What is Hawking radiation? Okay, in this figure, everybody, you see the event horizon of the black hole. This kind of radiation, everyone, is just, it happens around the event horizon. You see, everybody, we have particle and antiparticles in here. In fact, in 1970, it is stated that a classical black hole could radiate a thermal spectrum of particles using the basic principles of quantum field theory. In brief, this theoretical process works like this. So here, everybody, I described the process that Hawking described. In fact, just I explain it to everybody. So, but one can come and say, another physicist can come and say, no, this process is not true, and I have another scenario. This Hawking radiation can be through this process. So we can say, yes, you are welcome. If you have any idea, you are welcome. You can expand your idea, but you have to mathematically prove it. You have to physically prove it. In fact, this scenario has been proved. So how it works? In fact, this scenario, this Hawking scenario, works like this. Particles, as you can see in this slide, particle and antiparticle pairs are constantly being produced and rapidly disappear through annihilation. In fact, these pairs are a certain consequence of the, in fact, as I said, certain consequence of the uncertainty principle. So this radiation theoretically emitted from just outside of event horizon of black hole. These subatomic particles pairs, photons, neutrinos, and some massive particles arising naturally near the event horizon, it may result that one particle escaping the vicinity of the black hole, while the other particle of negative energy disappears into it. So what happens in here? In fact, the flow of particles of negative energy into the black hole reduces its mass until it disappears completely in a final burst of radiation. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. When it arrives at the mass of large asteroid, it radiates at the room temperature, and when it has the mass of a mountain, it radiates with about the heat of sun. And in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this is incredibly slow. The biggest black hole, everybody we know, might take up a Google year to evaporate. Okay, as you can see, the time, for this evaporation is a Google year. That is 10 to the power 100. And this time, unfortunately, is so long that when the last black hole radiates away, and nobody will be around to witness it, and the universe will have become uninhabitable, in fact. Okay, with this introduction, everybody, about the Hawking radiation, we have to look at uncertainty principle, because this radiation is just a certain result of uncertainty. And in quantum theory, everybody, this is an interested topic. That's why I'm talking about uncertainty principle right now. In fact, everyone, uncertainty principle, also called Heisenberg uncertainty statement, this statement, in fact, articulated in 1927 by this German physicist Werner Heisenberg, in fact, that it states that the position, as you can see in this figure, the position and the velocity of an object cannot both be measured exactly at the same time, even in theory. The very concepts of exact position and exact velocity together, in fact, have no meaning in nature. Ordinary experience, everyone, provides no clue of this principle. It is easy to measure both the position and the velocity of, say, for example, an automobile, because the uncertainties implies by these principles just for ordinary objects are too small to be observed. Okay, for example, in classical physics, for an automobile, a person, this kind of experiences provides no clue for uncertainty principle. This just works, this uncertainty principle, in fact, works just for an object are very small to be observed, are too small to be observed, such as atom and subatomic particles. In fact, just in that scale, this uncertainty principle works. Okay, the complete rule stipulates that the product of the uncertainties in position and velocity is equal to or greater than a tiny physical quantity that is known h bar. Okay, as you can see in this figure, this uncertainty in measurement of position and velocity must be greater and minimum equal to this constant, that is h bar, Planck constant. In fact, this quantity, h bar, is Planck constant, and it's about 6.6 times 10 to the power minus 34 joule second, okay? Only for the exceedingly small masses of atoms and subatomic particles does the product of the uncertainties become significant. So any attempt, in fact, to measure preciously the velocity of a subatomic particles, such as an electron, will knock it about in an unpredictable way, so that a simultaneous measurement of its position has no validity. In fact, everyone, this result has nothing to do with inadequacies in the measuring instruments, the technique, or the observer. It arises out of the intimate connection in nature between particles and wave in the realm of subatomic dimensions. In fact, everybody, this is because of wave-particle duality, the important topic. In fact, everyone, the uncertainty principle arises from the wave-particle duality. Every particle has a wave associated with it. Each particle actually exhibits wave-like behavior. The particle is most likely to be found in those places where the undulation of the wave are greatest or most intense. A quite accurate measurement of one observable involves a relatively large uncertainties in the measurement of the other. This is important. In fact, everyone, the uncertainty principle is alternatively expressed in terms of particles' momentum and position too, as you can see in this figure, okay? Momentum and position. In fact, delta P and delta X. In fact, the momentum of a particle is equal to the product, as we know in physics, of its mass times its velocity. And also, everybody, you know that the principle can be applied to other related conjugate pairs of observable, such as energy and time, okay? Another uncertainty principle that states that the product of the uncertainty in an energy measurement and the uncertainty in the time interval during which the measurement is made also equals h bar or more. I mean, it should be equal or greater than h bar, this Planck constant. And also, everybody, if we consider it more preciously, the same relation uncertainty holds for an unstable atom or nucleus between the uncertainty in the quantity of energy radiated and the uncertainty in the lifetime of the unstable system, as it makes a transition to a more stable states. Okay, everybody, there is a nice experiment, everyone, about uncertainty principle. In fact, everyone, there is an experiment that is called Schrodinger's Cat. Right now, everybody, in order to understand the concept of uncertainty more deeply, I would like to drive your attention to this experiment, the physics behind the Schrodinger's cat paradox. In this experiment, everyone, as you can see in this figure, you can imagine about this cat. Okay, there is a cat. We have a cat. It's placed. It is placed in a steel box along with a Geiger counter. There is a Geiger counter in it, and a vial of poison, as you can see, a hammer, and a radioactive substance. So let me just talk about this radioactive substance. In fact, everyone, when the radioactive substance decays, the Geiger detects it and triggers the hammer to release the poison. Okay, when the poison is released, that means the cat is deaf. It subsequently kills the cat. Okay, look at the scenario. I have to talk about the radioactive decay. In fact, everyone, the radioactive decay is a random process, and there is no way to predict when it will happen. Okay, physicists say that the atom exists in a state known as superposition, okay, but decayed and not decayed at the same time. Until the box is opened, an observer doesn't know whether the cat is alive or dead, because the cat's fate is intrinsically tied to whether or not the atom has decayed, and the cat would, as Schrodinger put it, living and deaf in equal parts until it is observed. Okay, in fact, we are dealing with two situations. In other words, until the box was opened, the cat's state is completely unknown, and therefore the cat is considered to be both alive and deaf at the same time until it is observed. Okay, if you put the cat in the box, and if there is no way of saying what the cat is doing, you have to treat it as it is doing all of the possible things, being living and deaf at the same time, because you are applying the superposition in here. Okay, if you try to make predictions and you assume you know the status of the cat, you are probably going to be wrong. But if, on the other hand, you assume it is in a combination, I mean, this here is superposition, it is in a combination of all of the possible states that it can be, all the possibles, I mean, states that is being deaf and alive together, you will be correct. Okay, immediately upon looking at the cat, an observer would immediately know if the cat was alive or deaf at the superposition of the cat. The idea that is, in fact, was in both states. In fact, it would collapses into either the knowledge that the cat is alive or the cat is deaf, in fact, but not both of them. So here Schrodinger, everybody, developed the paradox to illustrate a point in quantum mechanics about the nature of wave particles. What we discovered in the late, in fact, 1800s and early 1900 is that really tiny things, the point is here, everyone, please be careful and pay attention, that in fact, the really tiny things didn't obey Newton's law. So the rules that we used to govern the motion of, for example, a ball or a person or an automobile, a car, these rules, these classical rules, couldn't be used to explain how an electron or atom works. Here is a paradox. Excuse me. In fact, everybody, at the very heart of quantum theory, which is used to describe how subatomic particles like electrons and protons behave, is the idea of a wave function. A wave function, everybody, describes all of the possible states that such particles can have, including properties like energy, momentum, and position. Okay, in fact, the wave function is a combination of all of the possible wave functions that exist. A wave function in physics, as we know, for a particle says there is some probability that it can be in any allowed position. But you can't necessarily say you know that it's in a particular position without observing it. If you put an electron around the nucleus, it can have any of the allowed states or positions unless we look at it and know where it is exactly. That's what Schrodinger was illustrating with the cat paradox. In fact, in any physical system, without observation, you can't say that something is doing. You have to say it can be any of these things it can be doing even if the probability is small. In fact, for any event, in fact, there will be a small probability, even if it is very small, but it is existing. Okay, right now, everybody, I want to just talk a little bit about Einstein field equation. In fact, a certain result that proved the existence of black holes. Okay, in here, everybody, we see the Einstein field equation. In fact, in the general theory of relativity, the Einstein field equation, sometimes shortly it is called EFE, in fact, it relates the geometry of a space-time to the distribution of matter in it. Okay, this equation, this in the form of tensor, this equation for the first time published by Einstein in 1915. And as I told you, in the form of a tensor equation. And related the local space-time curvature, G mu nu and T mu nu with the local energy momentum, and a stress tensor with the space-time. So analogously to the way that electromagnetic fields are related to the distribution of charge and current via Maxwell's equation, okay, as you see in Physics 102 for our engineers, I'm talking always about Maxwell's equation. We know that in order to understand the Maxwell's equation, everybody, in the field of electromagnetic electric and magnetic field both together, we know that the distribution of charge and current relates to the Maxwell equation. Now in here, everybody, for Einstein field equation, this equation in fact relates the space-time geometry to the distribution of mass, energy, momentum, and stress. That is, they determine the metric tensor of a space-time for a given arrangement of stress, energy, momentum in a space-time. Okay, the relationship between the metric tensor and the Einstein tensor allows the Einstein field equation to be written just as a form of in fact, non-linear partial derivative equations when used in this way. Okay, everybody, you know that the solution of the Einstein field equation are the components of the metric tensor. The inertial trajectories of particles and radiation, that is called geodesic. In the resulting geometry are then calculated by just using the geodesic equation. Okay, in fact, everyone, as you see in here, in this Einstein field equation, so this is our G mu nu Einstein tensor, and G mu nu, this small one, is metric tensor, gamma is cosmological constant, and K is just the Einstein gravitational constant. I mean, here we have, this is written in terms of G, which is gravitational constant, and speed of light. In fact, everyone, in order to solve this equation, in fact, it's not easy to solve that equation. I can say you that exact solution for the Einstein field equation can only be found under simplifying assumptions such as symmetry. Okay, and sometimes, for example, the simplest solution of Einstein field equation is Schwarzschild's. Okay, in order to solve this equation for Schwarzschild's case, you see in here in this equation, everyone, there is some assumption. The first assumption is that we assume it is just in fact a static sphere, spherically symmetric. There is a spherically symmetric for this black hole. We assume in here Schwarzschild's black hole, everybody, is the first solution and the simplest solution of Einstein field equation, in which it is assumed that charge is zero. It is a static, that is, there is no rotation. This is just an assumption. And also, for example, charge is zero in this case. A static, spherically symmetry, and gamma, this constant, everybody, here, a cosmological constant is assumed to be zero in here. Okay, after all this assumption, this physicist Schwarzschild found a metric. In fact, he mathematically proved that there must be a black hole with this metric function. There are, everybody, right now, this is the first one I say, there are another lot of many solution of Einstein field equation with different, in fact, assumption. For example, recently I worked out about a paper that is about black string. Black string, everybody, is just, as I tell you, this Schwarzschild's black hole is just a spherical static symmetry. We assume that the black hole has the form of a sphere. In fact, with just this assumption, we assume that black hole is formed as a sphere with the spherical symmetry. We found this solution. There are another solution, everybody, a lot of many different solutions when charge is not zero. For example, as I'm telling you, in a paper, I've published a paper about black string. In that paper, everybody, we just look at the cylindrical solution of Einstein field equation. In fact, black string is just the cylindrical solution of Einstein field equation. And in that solution, we just assume there is cylindrical symmetry. Okay, it has been solved for uncharged black holes and charged black hole, both of them. Another solution, for example, term Rindler acceleration is added to the Schwarzschild's metric. For example, if something added in here, but the momentum energy tensor, the solution of energy momentum tensor should be satisfied. Okay, you have to check all the possible things. Okay, for example, in Gromiller black hole, everybody, cosmological constant is not zero, and there are another solution for that. There are a lot of papers that published about this subject. Something else, recently I'm working about non-linear electromagnetic, in fact, charged black hole with non-linear electromagnetic field. This is another interesting topic, and in fact, there are many, I can say you that it's just like an ocean, and when you go inside, you will go further and further, and you will have a lot of things to do. Okay, I think that's enough. I will not push you anymore. Just at the end of today's discussion, everybody, I prepared another video that it might take just 2 or 3 minutes. It's a nice video, everyone, that is about, in fact, size of universe. So I would like to drive your attention and watch this video together. Let me get started. Yes, this is about the size of universe, everybody. 10,000 kilometers when you go way away, Earth and Moon lunar orbit, 1 million kilometers, 100 million kilometers. Kepler belt, 10 billion kilometers, everybody. When you go way out, 1 light year, 10 light year, 100 light years, 10,000 light years, spiral arms, Milky Way, galaxy neighborhood, 1 million light year, cosmic web, 1 billion light years. This is the distance from Earth. And vice versa process. We go toward vice inverse process. And then right now we look at the atom and subatomic particles. Let's go inside. Okay. Vessels, blood vessels, micrometers, 10 micrometers. Chromosomes, 1 micrometer, 10 nanometers. Chromosome, fiber, nanometers. This is just the scale. Atom, 1 nanometer. Okay, we reach to oxygen atom. Inner electrons inside. Let's go. Picometers. Nucleus, femtometers, 10 to the power minus 15. And quarks, up and down. Okay, everybody, thank you for your attention. This is the end of my presentation, and I'm here. Do not hesitate to ask your question.
Thank you.
You are welcome, Hocam, Dilber Hocam. Your microphone is closed, Dilber Hoca. Would you please open
Now
it?
it's okay now?
Yes, yes. Thank you so much.
I would like to thank you very much because of
Thank you so much, Hocam. I would appreciate you for this
like
preparing all of this moderation. Thank you so much.
It was very interesting. I refreshed my own knowledge about physics. I think it was excellent. Thank you very much.
Thank you so much. Thank you.
Is there any question? Let me check the comments. Okay, if you have a question, you could just write it in the comment section, please. I think it was very refreshing for me.
Thank you so much, Dilber Hocam. It's very kind of you. Thank you so much for your interest. Thank you so much.
Akbar Abbasi said that thank you so much for this interesting topic.
Thank you so much, Akbar Hoca, Professor Akbar. Thank you so much.
Thank you very much for this.
Thank you, İlker Hocam. How are you doing? I hope everything is okay with you, İlker Hoca.
Çetin Özkan, is there any border of
Merhaba Çetin Hocam, you're welcome.
He has a question, I think. Çetin Özkan. Is there any border of our universe or it is open universe?
It is open universe. 100%. Of course, there is another field that is talking about expansion of universe. It is 100% open, Hocam, and human, I mean, we are never, in fact, it is not possible to understand it 100%. This is what we know about the dark matter and dark energy. What we know right now, it can be just less than 1% of the universe. This is, in fact, human, unfortunately, can never understand it. It is out of our imagination.
Dr. Berna says, it was an amazing talk.
Hello, Berna Hocam. How are you? Thank you for your interest, Berna Hocam. We are waiting for you. We miss you.
There is no more. question or comments? Yes, I was very impressed, hocam. Thank you very much.
Thank you so much. Thank you so much.
Hadi Sadaraka, thank you so much, doctor. Will be the PowerPoint be? I think we are.
Hello, Fadi Hocam. Yes, thank you so much for your interest. Of course, there is. I will send you via the email. Thank you.
Uzun Tunç Yürek said
thank you so much, Uzun Tunji Rek. Thank you so much, Professor Uzun.
Thank you. I think we have to do it like more, this kind of presentation.
Yes. I will do next semester another topic. Yes, this is my interest. I will do another one next semester, in fact, about another topic. It can be about the parallel universe, in fact, another interesting topic.
Very interesting topic, yes, indeed. Thank you very much for all coming, and thank you very much, especially to you, Dr. Fatemeh.
Thank you so much. Thank you.